So when we discussed Faraday's law, we mentioned that the EMF that's induced is equal to the change in the flux in a time period. And then that's going to be negative. And so I mentioned to you we'd come back and talk about Lenz's law, which is where the negative sign comes from. Lenz's law says that any induced magnetic field will always oppose the change in the magnetic flux. So if we change the magnetic flux, there will be an induced EMF, and that EMF will be induced in such a way as to produce a magnetic field that opposes the change in magnetic flux. Now that sounds a little bit confusing, but if you think about it, if we have a field and then we've got this loop, and then we think about the current that's induced, we can figure out the direction of the current that's induced. So let's take a particular example. So here's an example. We've got a ring where the flux is upward, and then we increase. So there is a change in flux here in time, and so we get an EMF induced, and it's going to be induced in such a way as to oppose the change. So we are increasing the upward field, and so the current itself will create a field that is directed opposite to that. So the current is going to direct a downwardly directed field, and so if we use the right-hand rule, we put our fingers in the direction of the field. So in the center of the loop, our fingers go down, and as we try to grab the loop, our thumb then is pointing so the induced current comes around the loop like this, and that will induce a current that opposes the change in flux. So here's another example. We've got that same initial upward flux, and so now we're going to turn the field down so that the flux decreases. Well, in this case, the center of the loop used to have more field lines, and now we're taking some away, so the current is going to be induced in such a way as to get those field lines back. It's opposing the change. So if I want upwardly directed magnetic field, then the current's going to go around the loop this way, and that induced current is opposing the change in the flux. So the EMF that gives us the current is opposing the change in the flux. So in this diagram, we have three regions. We have a region around the dotted box where there is no magnetic field. We've got a region on the left side where the magnetic field is directed into the screen, and we've got a region on the right side where the magnetic field is directed out of the screen. So we've got this conducting loop, and we want to take our conducting loop and we're going to move it. Anywhere we move it out here where there's no field, I get no current, because there is no change in the flux. However, when I get to position 1, I go from no field to some field, and so that means the flux is increasing. If the flux is increasing, then the loop itself wants to oppose that increase. And if I oppose the increase, then what I want to do is generate a field so that it is in the opposite direction to the external field. And so to do that, I'm going to put my fingers in the direction of the field, which is pointed out of the screen in the middle of the loop, and my thumb then moves around, and I've got a counterclockwise current. Once the loop is completely inside the field, at position 2, anywhere I move it around inside of this field, the current will not be induced because there is no change in the flux. It's not until I get to position 3 and I start adding in some field that is upwardly directed and removing some field that is downwardly directed. And what I want to do, what Lenz's law says, is I want to oppose that. So I'm opposing a decrease in downward directed field. So I'm going to induce some downwardly directed field. I'm also opposing this increasing upwardly directed field, and that's also downwardly directed field. So if I grab a hold of that loop, so my fingers are pointing up through the center, and I'm looking at, down through the center, then the current will be moving clockwise. Just like in position 4, there is no current, because no matter where I move it around in there, the change in flux is equal to 0. As it exits here at position 5, I go from upwardly directed field to no field, and so the flux is actually decreasing. I want to oppose that decrease, and so to do that, the current is going to set itself up in such a way as to have field lines that match the field it's leaving, trying to maintain. And so I push upward through the middle of the loop with my fingers, and the current then is in the counterclockwise direction. So Lenz's law is really a conservation of energy idea.